Welcome back all of you. From the last class, we started discussing about 2D NMR. In the last class, I introduced 2D NMR, where I explicitly mentioned 2D NMR is different from 1D NMR in the sense we have two time periods. General sequence for any 2D NMR, I said, consists of a preparation period, evolution period, mixing period, and a detection period. And detection period time is always constant. You acquire the data in a conventional 1D spectrum, way you acquire for 1D spectrum. Evolution period, the T1 is incremented systematically. For every T1, you are going to create an FID. You are going to have a time domain data. You can create as a function of time, incremented T1 a pseudo free induction decay. You create a time domain data during the evolution period, and you have two time domain data. One in the detection period is always constant, and a pseudo FID created in the evolution period. Do the double Fourier transformation, you are going to get two frequency domain spectra, double frequency spectrum. So that is what we discussed about the 2D NMR. And then of course, it is not restricted to 2D. We can go to n number of n dimensions we can have. You can have 3D, 4D, etc. But what defines dimensionality? N time periods. N time periods has n dimensionality. N different time periods should be there. In that n time periods, one of them is a constant. Last time period we acquire the data is constant. And the remaining n minus 1 time periods you are going to vary it systematically and create its pseudo FID in each of them. So for n time periods, you do n dimensional Fourier transformation, you are going to get an n dimensional frequency domain spectrum. That is NDNMR. And then now the question is, how do you choose which dimensionality you require? It depends upon the molecular size. And of course, as you go to higher and higher dimensions, I told you it takes enormous amount of the instrument time. I said 1D NMR for a reasonably small molecule, even reasonably big molecules, in the present day spectrometer with so much of sensitivity gained because of high magnetic field, etc., various techniques, you can get 1D NMR in less than 5 minutes. On the other hand, if you go to the 2D NMR for the same molecule, you may take several minutes, maybe 30 minutes, 40 minutes, 50 minutes like that. If you go to 3D NMR, it may take several hours. If you go to 4D NMR, it may take days, or even if you go to 5D NMR, it may take even weeks. So the dimensionality as you increase, the time required to acquire the signal also keeps increasing. And of course, it depends upon the molecular size. Dimensionality also depends upon molecular size before you choose. For example, 1D NMR for small molecule of small molecular weight of let us say 300, 400, etc. Just 1D NMR is sufficient. You can simply analyze such molecules. We saw in the analysis of 1D spectra in the previous classes. One or two examples we took. We analyzed the 1D spectrum. If you go to 2D NMR, okay, molecular weight as an example of the protein which is taken, it could be a 0 to up to 20 kilodalton. 3D NMR can be slightly, you can extend it. 4D NMR, of course, you can go up to 40 or 50. Beyond that, you need 4D NMR. In addition to that, you require special experiments also. So as you keep on increasing the dimension, you will get the increase in information content, and at the same time, you can also get the resolution because you are spreading the information in different dimensions. That's what we discussed. Now I want to tell you one thing today. Fine, what is the benefit of going to higher dimensions? The benefit of going to higher dimension is like, I can show you like this. Let us say we have couplings, which is already present. I also have chemical sheet for two different nuclei. I have given different colors, blue and red. And couplings are very small, interaction strength is small. Small balls are written there. Now let us say the 1D spectrum, I have not of different nuclei, let us say different chemically inequivalent spins, you can call it. Because 1D spectrum, different nuclei you cannot get in the same 1D spectrum. So we call it different nuclei, different chemically inequivalent nuclei of the same molecule. Now we have different protons and you have J couplings, everything is overlapped. It is a complex spectrum. So if you want to analyze this 1D, it is fairly complex. You need to spend a lot of time. What on the other hand we can do is, go to 2D. I can do 2D experiment in such a way, I can resolve this on the basis of the sizes. Let us say I can have J coupling which are smaller in strength and in this dimension. All this type of black and red balls what is written here, they are of the same size. So on the basis of the size, I can divide this information in 2 dimensions. So I can put all the J couplings which are small interaction lengths, which is apparently by small type ball sizes, that can be here. This is one way, but still there is a complexity here, because different chemically inequivalent protons, different spins are overlapped here. Still resolution is poor, although you have got already resolution, some resolution by going to 2 dimensions. But to increase this further, we can go one more dimension we can do. We can go to 3D NMR. What we do is, see, in this dimension we change the color of the balls here, that is the J coupling here. We have one chemical shift of proton here, one type of protons, and other type of protons are here. Now these black balls, red balls and blues, everything got separated in 3 dimensions. Look at this, it was all clumsy, everything was overlapped, and it was complex spectrum. It was very challenging to analyze. 2D helped us a bit in resolving the information, getting better resolution. If you go to 3D, even better, you go to better resolution you are going to get. That is what happens. As you go to higher and higher dimension, you get benefits of resolution, benefits of information content spread in different dimension. Easily you can extract the information. So it simplifies the spectral complexity as you go to higher and higher dimension because of higher dispersion. Dispersion will be there. You spread the information content in different dimensions. Okay. With this, now if I had to do 2D NMR experiments or any 2D or 3D experiment, we will strict all our discussion to 2D only, we do not touch upon 3D in this course. We will say a broad classification of 2D experiments, in my view, it is my suggestion, my way of looking at it, can be into 2 things. One, I call them as correlation experiments. This correlation experiment is the one which has information spread in 2 dimensions, or 2 dimensional information can be correlated. I can have one here, one information, and I have another information in other dimension, but I can correlate the information from this dimension to this dimension. Either I can correlate chemical shift, it will be chemical shift of homonuclei, or chemical shifts of heteronuclei. I can correlate. If I know the chemical shift of one of the protons here, I want to know if that proton is coupled to another proton, I can have the chemical shift of that information, that proton here in this dimension. If I know I have carbon 13 here in this dimension, let us say, I have a proton here, I can have the proton chemical shift here and carbon chemical shift here in this dimension. Then I know which carbon is attached to which proton. So I can have this correlation information. That is one type of experiment. Basically we can have some experiment like TOCSY, COSY, 1 or 2 examples we can touch upon in this course. Remember, I am going to touch upon this briefly. This was discussed in depth extensively in the previous course. For the benefit of those who did not take the course, I am just touching upon when I come to COSY and TOCSY, 1 or 2 simple examples. Now other thing is resolved experiment. The resolved experiment is another type of experiment where the information content is spread into 2 dimensions. That is the resolution. Here you are correlating, you are resolving, separating out the 2 information. For example, J resolved information, J resolved experiment. J resolved, you have chemical shift in 1 dimension and J coupling in another dimension. That is also possible. You can do that. Okay, there are one type of experiments. But now both these can be homonuclear and heteronuclear also. It is both resolution resolved experiment or correlation experiment you can design in which both the dimension can be homonuclear. Let us say proton chemical shift here, proton chemical shift here, that is one homonuclear, or proton couplings here, proton chemical shifts here, or proton couplings here. That way they are homonuclear experiments. You can also have heteronuclear experiments. For example, you can have carbon chemical shifts here, proton chemical shifts here, nitrogen chemical shifts here, carbon chemical shifts here, or proton chemical shifts here and carbon chemical shifts here, carbon proton couplings here. All those things experiment can be designed. These are all common experiment, maybe 1 or 2 we can touch upon in the as quickly as possible we will go. For example, for homonuclear experiment it is called COSY, TOCSY, there are correlated experiments. J resolved is a resolved experiment. Heteronuclear experiments are heteronuclear correlation, HSQC, heteronuclear single quantum correlation experiment, heteronuclear multiple bond correlation, and also heteronuclear J resolved we can have. varieties of experiment. Remind you, this is only tip of an iceberg. If you go to the literature of NMR, several hundreds of such experiments have been designed by various stalwarts are there in NMR, various experts. They have designed varieties of experiment which benefits all of us. And we are not going to touch upon everything because it is going to be a big ocean. Only couple of 1 or 2 simple experiments. We'll see how it works, what we can do, what information we can extract from that. That we will work out in this class. Okay. So now you can ask me, okay, what are the other things we can get in the 2D NMR? I can correlate this one. I can correlate chemical shifts, homonuclear. I can correlate heteronuclear chemical shifts. I resolve the 2 parameters, chemical shifts and J coupling into orthogonal dimensions. What else we can get from NMR 2D data? If I get a 2D spectrum, many things you can get. I can get the coupling pathways. I can get the coupling constant, short range, long range coupling constant. I can get reduced dipolar couplings, RDCs I can measure. I did not introduce dipolar coupling, maybe when I go to solid state NMR. Magic angle spinning and cross polarization, I will discuss something about dipolar coupling. But reduced dipolar coupling is another thing where you can have a partially averaged system, oriented system, where dipolar couplings are partially averaged and you get dipolar couplings you can measure. That is reduced dipolar coupling. Remember we discussed when I gave the NMR parameters, internal interaction parameter, I said this is about dipolar coupling also is one of the important parameters which gets averaged out in the solution state. I said that it is depends upon the distance between 2 interacting spins. It is spatial interaction. It is not through space, not through bond. That is what I said. We can get information about the NOE. You can get information about the diffusion. You can get information about the relaxations. Varieties of things. If in all these things you can have homonuclear information, heteronuclear information. Imagine varieties of combinations you can think of. And if you go to solid state, all 2D experiment what you can do in liquid state. Similarly, there are varieties of 2D experiment designed for solid state also, depending upon the type of interaction parameters that are present in solids. That is also possible. For example, chemical shift anisotropy. I told you in NMR all the parameters are anisotropic. Chemical shift is anisotropic, J coupling is anisotropic, dipolar coupling is there, and quadrupolar coupling, all these are anisotropic. The chemical shift anisotropy, what happens in the solution state gets averaged out. But if you go to the solid state, it is present. We can extract that information. That gives you some information. If you get chemical shift anisotropy from the NMR spectrum, that gives you information about the charge distribution at the site of the nucleus. I can measure the dipolar couplings. The advantage is, if I get the dipolar couplings, I can get the distance information. See, so many information content are there. All this can be extracted by varieties of 2D experiment. The 2D experiment is really very useful. Voluminous amount of information is there, and a lot of experiments are available. You can derive all those things by designing varieties of experiments. Remember, all these things what I said is only tip of an iceberg. There are many things we can derive, many information. So there are plethora of experiments, plethora of information content that you can determine from the 2D NMR spectrum. Okay. Now, the NMR spectroscopists are very crazy people in the sense they always design an experiment, give a name for it. That is the way. Depending upon the pulse sequence, you can design a pulse sequence based on the information you want to derive by understanding the spin dynamics. That is what most of the stalwarts of NMR people have, NMR spectroscopy people have done all over the globe. They have been doing that. And then give an acronym for it, a name for it. For example, COSY means correlated spectroscopy. It correlates to information. It can be homonuclear COSY or heteronuclear COSY. In the case of homonuclear COSY, we correlate to chemical shift information between 2 coupled protons. Okay, that is called COSY. SEXY. SEXY is another experiment called spin echo correlated spectroscopy. NOSY, nuclear over-Raman effect spectroscopy. That is where you get the information about 2 nuclei which are close in space, where NOE transfer is going on. One nuclei because of irradiation, we discussed about NOE. You irradiate one of the protons, you see the change in the intensity of the other one. So NOE information can be obtained by NOE. There is also called ROSY. ROSY is the rotating phase over-Raman effect spectroscopy. We can have the decay of Cauchy, double quantum filtered Cauchy. These are some I mentioned only less than 1% of NMR spectrum, the experiments that are available in the literature. So many are there. Several hundreds of such pulse sequences are there. They have been given acronyms. Just to give you the idea, to remember, to see what type of experiment, how the acronyms are given, I mentioned these things. Cauchy, Sexy, NOC, etc. Further going ahead, we can have HSQC experiment, heteronuclear single quantum coherence spectroscopy, HSQC. Here you are going to correlate two different heteronuclei based on the one bond coupling between them. And also you can have HMBC, heteronuclear multiple bond correlation, multiple bond, you can say coherence. That is, you are correlating proton or carbon which are separated by one bond, not one, 2 or 3 bonds away. Similarly, all this experiment can have gradient versions. We discussed a lot about gradients. Remember, pulse field gradient for selection of the coherent transfer pathway, etc. There are varieties of such experiments possible by using gradients. So each of these pulse sequences generally is there. People have modified accordingly for the information retrieval. Every time when it is modified, you get additional information or improve the sequence, you get better by either to get the better signal to noise ratio or better resolution, etc. Like that, people have designed number of experiments. You can also have a DOSI. DOSI is the one diffusion ordered spectroscopy where you can get the diffusion information in one dimension. If there is a mixture of molecules, you can separate them out based on the diffusion coefficients in a solution state. That is also possible. So imagine the type of experiment are there. You can even touch upon DOSI if there is a time. I don't know how much time is left. Still I have to cover a lot of things about solid state NMR, 2D, MQT, if possible pure sheet, varieties of things are there. I don't know whether we have time. If there is time, we will touch upon that. Now, what do these pulse sequences do? What these pulse sequences do? What does each experiment do? Each of these experiment has its own pulse sequence. When I say Cauchy, immediately it comes to my mind. It has two pulse sequence, 90 T1, 90 T2. It comes to my mind. Similarly, I can think of Toxi. Okay, that is one way. Heterochemical correlation, that is one thing. HSQC, one pulse sequence. All these experiments has its own pulse sequence. All for NMR spectroscopies. If you simply reel out that name, HSQC, Cauchy, HMBC, etc., the type of experiment, the pulse sequence and information content, that information that is retrievable from such experiment suddenly comes to their mind. So each experiment has its own pulse sequence. And combination of pulse sequences are there. Sometimes couple the experiment to derive information. For a HSQC is there, HSQC Toxi I can make. I can combine HSQC sequence with Toxi, make it a 3D experiment, HSQC Toxi. Like that, you can have combination of the pulses, combination of experiments, and again it could be both homonuclei and heteronuclei. You can have one proton in one this thing, you can apply pulses on proton, apply pulses on carbon, and you can have vary the delays in this different experiment to get different information, and change the magnetization to different axes, and bring them into contact in different mixing periods, so that different type of information is transferred between the spins. Varieties of all experiments can be designed. So all this, each of these experiment has its own pulse sequence. And usually when we have a delays, especially we discussed about inept, where this we can have the delays tailored to a specific coupling constant or over a small range, like 1/2j. Remember we discussed it is going to in phase will become anti-phase. We observed that at exactly 1/2j. When two protons are coupled or two spins are coupled, both homo or heteronuclear, we observed that when you bring the magnetization to the XY plane, they start fanning out. At exactly 1/2j, if you will find out, we saw that both by vectorial diagram and also by product operators, we found out it is going to create antiphase magnetization. Like that, using those information, we can design the particular experiment, so that in this experiment, for example, I tailor it such that it could be implemented in a polarization transfer experiment to transfer information from one spin to other spin. So, a variety of such information is available in each of this pulse sequence has its own experiment. Each experiment has its own pulse sequence. Now, the pulse durations, that is also very important, that creates coherences sometimes. It transfers coherences from one spin to another spin. It allows the modification of one and encode this information into other spin, that also is possible. And you do all those things up to the last time period where you apply the final detection pulse to detect the signal and start collecting the data in the detection period, where you collect the real FID, you record the FID in the time domain T2, or okay, since we are discussing only 2D, in the T2 period. So, this what always happens, all these things, pulse duration is very important, that decides varieties of information which you want to derive. Another important thing is, in each 2D experiment, the relationship between two or more spins within the molecule are established by transfer of magnetization between the spins. If I want to establish a relation between two spins, let us say in a given molecule, I have one proton here, another proton next to it. I know there is a J coupling between them, there is an interaction through covalent bond. If I want to find out whether this is coupled to this, I can do a correlation experiment where there is a transfer of magnetization between one spin to another spin, that gives me a peak in the 2D spectrum. So, all these things what happens in each 2D experiment, if you are depending upon the information which you are trying to derive, the relationship between the two spins or even more spins within the molecule are established only by the transfer of magnetization. Of course, that is another thing, very important thing. The transfer of magnetization is one thing which gives us the relationship between two spins. Next, if you go to the magnetization transfer, the mechanism in which it transfers, mechanism in which magnetization gets transferred is different for different experiments. Okay, just to tell you, we can do an experiment called transient NOE. We discussed about steady state NOE also. We can have an experiment on transient NOE where Z magnetization transfer takes place via NOE. You can have an inept, remember we discussed inept where antiphase magnetization transfer from one spin to another spin. This is antiphase to antiphase coherence transfer. Here J coupling is important, that is what we discussed. J coupling is the one which creates antiphase coherence, and that is responsible, antiphase to antiphase coherence is possible only through J coupling. So, in experiment like inept where the polarization transfer experiments are there, this magnetization transfer or polarization transfer takes place from antiphase magnetization, antiphase coherence to antiphase coherence. TOCSY is another experiment which we will discuss. It is multiple in-phase to in-phase coherence, that is another very interesting thing. Again it happens via J coupling. Coherence transfers take place via J coupling. It is in-phase to in-phase transfer. ROSI is a rotating over-Raman effect spectroscopy where the NOE transfer takes place in the XY plane, that is during what is called a spin lock. Maybe even I will explain spin lock when I come to solid state, where we discussed a lot about, we will discuss about cross polarization etc. I will discuss what is spin lock etc. at that time. Okay. And each of these magnetization transfer mechanism can be applied to create a specific 2D experiment. Remember, I can have a special, the magnetization transfer mechanism, if you know, I can create a specific 2D experiment. For example, COSI, correlation transfer information, where the magnetization transfer takes place to correlate two protons which are coupled among themselves, or two or more protons coupled among themselves. Heteronuclear correlation of two chemical shapes between two heteronuclei or more heteronuclei. HSQC, single quantum coherence, where it is inverse experiment. I will discuss about inverse experiment where it is used as single quantum. External multiple bond correlation, multiple bond coherence, NOC, nuclear over a surface, ROSI, TOCSY, all these experiments are designed. In each of them, the way the magnetization transfer takes place is specific to particular each of these experiments. That is how different pulse sequences are designed in NMR. Okay. So, remember, Each pulse sequence is designed where the mechanism of the magnetization transfer is specific to each of these experiments. Okay. Now, common two-dimensional experiment which everybody uses. For example, most of the time very sophisticated 3D experiments or very sophisticated 3D experiments, specially designed experiment, that is the research of NMR spectroscopies for particular information. Commonly, if a chemist or biologist who they want to use simple molecule just to characterize their molecules, they don't need to go to very high sophisticated latest state of the experiment for deriving information. Sometimes simple experiment like COSY, phase sensitive COSY, DQF COSY, soft COSY, relay COSY, TOXY, inadequate or NOSY, ROSY, J-resolve, these common experiments is suffice to get their results. You don't have to go to complex 2D spectrum, 2D experiment. So, common to homonuclear 2D experiments, where is I am talking about homonuclear, are these things: COSY, TOXY, NOSY, ROSY, J-resolve, etc. Even inadequate, etc. Heteronuclear 2D experiments. Similarly, like homonuclear, we can also have heteronuclear, where heteronuclear correlation is more or less nowadays nobody uses because inverse detection has come, HSQC we use. COLAC, correlation, long range correlation experiments. Heteronuclear relay is homonuclear relay experiment level. TOXY is also called HOHA, homonuclear Hartmann-Hahn. Same way, heteronuclear relay is called HEHA, heteronuclear Hartmann-Hahn experiment. So, heteronuclear J-resolve experiment is also there. These are common heteronuclear experiments. As I said, these two experiments takes enormous amount of time. Nowadays, people don't use this type of experiments at all, and for that new experiments have been designed. They are called inverse experiments. Their example, HSQC. It is an experiment, it is heteronuclear single quantum correlation, where you can correlate the chemical state information to heteronuclei, for example carbon to proton, which are single directly bonded, one bond correlation. This is called that experiment. How it works we will discuss later. It is called heteronuclear single quantum coherence experiment. HMQC, heteronuclear multiple quantum coherence. HMBC, heteronuclear multiple bond coherence. So, all these experiments are inverse experiment. What is an inverse experiment? When you go further, we will discuss later. I will come to HSQC and etc. We will have an in-depth discussion about this type of experiment later. It's especially HSQC and HMBC. How do you get the information? We will discuss. Okay. And before we go further, we should understand how do you interpret the spectrum. You may be an expert. You would have understood how the pulse sequence works. You would have done an experiment, but you must interpret the spectrum. You should know how to interpret the spectrum to get the information. You to retrieve the information from the two-dimensional spectrum. How do we interpret generally is given like this. General interpretation, I mean it is not specific to any particular experiment, more or less general information. Let us say I get a 2D spectrum like this. I get a 2D spectrum and I have a peak here. It is 2 dimensional, this is F2 dimension, this is F1 dimension. And if you look at it, I get a peak here and I go here, draw, correlate here, it comes at 80 hertz here. This is in the F2 dimension, and in the F2 dimension I draw a horizontally a line here, it comes at 20 hertz. So, I see a peak which in the F1 dimension corresponds to 20 hertz. I see a peak, the same peak in the F2 dimension, I read it as 80 hertz at 80 hertz. So, this one peak in the 2D spectrum I read in the F1 dimension is coming at 20 hertz. I read the same thing in the F2 dimension coming at 80 hertz. Okay. So, the signal what you understand is that is evolved during the T1 period with a frequency of 80 hertz, that was in the T1 period, it was at 80 hertz. During the mixing period something happened for it. It so happened the signal was transferred some way by some mechanism by some polarization transfer method to another spin this itself evolved at 80 hertz during T2. The signal what happened which evolved at 20 hertz in T1 period. During the mixing time the same what happened to the same signal which was transferred in some way to another signal which appeared at 80 hertz. The same signal transferred to another one which evolved at 20 hertz in T1 which appeared at 80 hertz in T2. That is how you have to interpret. The peak which you appear this here which is at 20 hertz in F1 and 80 hertz in F2 means during T1 period it was at 20 hertz, it was evolving at 20 hertz. In between during the mixing time something happened, it started giving its magnetization to another spin and then evolved at 80 hertz. That is the interpretation. Okay, you have to understand that. So, like let us say you go to the other one. Now it is another interpretation. Now I have a peak here. Draw a line here to T2 dimension. You see it is at 20 hertz. Same peak here you see at 20 hertz. It means I have a peak which appears in the F1 dimension at 20 hertz. In the F2 dimension also it is at 20 hertz. That means the signal evolved during T1 with 20 hertz, it remains unaffected. It did not change at all. It did not give its energy to or magnetization another spin. It remained unaffected and continued to evolve at 20 hertz during the T2 period. That is the interpretation. Go to the next one. Now I have a peak at 20 hertz in the T1 period and I have a peak at 20 hertz and 80 hertz both in the T2 period. T2 period now you see I have two peaks in this dimension, this and this. In this dimension I have only one peak. So, the F1 dimension I have one peak at 20 hertz. In the F2 dimension I have two peaks at 20 hertz and 80 hertz. What do you understand this? The signal at 20 hertz in T1 evolved during T1 with a frequency of 20 hertz, remain unaffected. Also that remained it affected, but it evolved at same frequency. Also what it means is it transferred part of its magnetization to another signal, another spin, which is during mixing time, which is at 80 hertz. Understand? The peak or signal which was coming at 20, which was evolving at 20 hertz during T1, it continued to evolve at 20 hertz during T2. In addition to that, during the mixing period, gave part of its magnetization to another signal or another spin, which evolved at 80 hertz during T2. This is what you have to understand. You have to interpret the 2D spectra like this. Okay. So now, what I am going to do is next I will understand a particular 2D experiment. Since the time is up, I am going to stop it. But you understood in this class, we discuss varieties of pulse sequences are possible. We understood how we have broad classification of experiments, homonuclear correlated experiment and resolved experiment. Again both can be homonuclear and heteronuclear. And then we understood each pulse sequence has its own way of magnetization transfer during mixing, its own way to correlate the information, get the information. So, somehow one spin gives information, another spin in some way, some mechanism of transfer is there. And we understood how it happens for example, during inept, antiphase to antiphase this thing, and in the case of the taxi, in-phase to in-phase in the X-ray plane, all those things we understood. In the case of the NOC, we have a Z magnetization, all those things we discussed. Okay. So, and each of these has been given names. There are umpteen number of pulse sequences available, umpteen experiments. Each experiment is designed to derive a particular information. Okay. So, what are the things, how you design it, what is important is the pulses and the delays. You have to tune the delay, tailor it for a particular information you derive, and otherwise you understand from product operators also we understood, we know how in a given sequence when you apply pulse and delays how the magnetization evolves. Understand the spin dynamics and design an experiment to get the information what that you want to derive. That is possible. So, we saw varieties of common experiment like COSY, TOXY, etc., or heteronuclear experiment like heteronuclear correlation, HETCOR, HSQC, etc. Like we also have inverse experiment which is nothing but HSQC, HMBC, HMQC, etc. And we also understood how to interpret the 2D spectrum. If I have a peak, let us say at some frequency in F1 and some frequency in F2, what does it mean when it what is that frequency of its evolution in the T1 period, what is its evolution frequency in the T2 period, during the mixing period, whether it has given energy, coherence to other spin or not. You can understand from this by looking at the 2D spectrum. That is how you have to interpret the 2D spectrum. So, with this we will go to special experiments, try to understand few of these things in the next class. So, I am going to stop it here. We will come back and continue with different type of experiment, starting with the basic experiment like Cauchy from the next class. Thank you very much.